Okay, so we stop at 2 minutes. It's at 2:20. Let's stop. So in tic-tac-toe, you guys know there's a function called value, but is there a Q function? How does that work? Let's see what people said. Reveal. Okay. All right. Most popular answer was we can write Q of S comma A equals V of S with A because we know what happens when the action is played. That is absolutely correct. So if you pick that one, very good. It means you've been looking at the homework. So in the tic-tac-toe that you guys have, when you are given the choice of the action, there's always 9 possible actions in tic-tac-toe. It happens that some of them are illegal if there's already a piece there, but there's 9 possible actions. So you're given an array with 9 things that would happen if you chose that action. So the array number 0 is what happens if you choose action 0. The array number 1 is what happens if you choose action number 1, and so on and so on. And so the Q function really is a value function, right? If you know exactly what happens, it's just saying what would happen in that situation. You can do it with a value function. In general, in reinforcement learning, it's important to have Q functions because we can be in situations where you don't know what would happen in an action, right? So imagine you're a robot and the action is like spin your wheel for 1 second. What happens when you spin your wheel for 1 second? Do you go forward? Do you turn? We don't know. We're going to try it out and see. So in more general situations, you won't know what happens. But in tic-tac-toe and pig-tac-toe, we have baked it in by giving you the set of all the things. Actually, so what I've said is perfectly true for tic-tac-toe and is sort of mostly true for pig-tac-toe. But there is one exception. Does anyone know the one situation where there is kind of a Q function that will happen? You won't be able to write this. Yeah.
When you choose to roll again.
That's right. When you choose to roll again or not, you will not know what will happen on the other side of rolling again or not, right? Because if the roll comes out one way, one thing will happen. If the roll comes out the other way, another thing will happen. Fortunately for you, you do know the probabilities. So you were told that the dice has 6 sides, and a 1 and a 2 mean you failed, and a 3, 4, 5, 6 means you succeeded. So you will not be able, in pig-tac-toe for the final project, you will not be able to just replace Q entirely with V, but maybe you can think of what you're supposed to do. I won't say any more about that for now. For now, let's just focus on getting tic-tac-toe done before we think ahead to pig-tac-toe. So that's very good. For the rest of today's lecture, there's a couple things I want to do. Let me, first of all, I got to change it only lets me do one window at a time right now. So I got to change the window to the other window. I guess I got to open it first. Okay, well, let's do this one. We want to do notability. Okay, so a couple different things we want to do, and one of them is take what we learned for TD learning, temporal difference learning, from last class. And last class it was only for learning a value function, so it was policy evaluation. Learn V. And some of the things we're going to do today, one thing is we're going to do policy improvement. Policy improvement. And so we're going to learn the Q function. Learn the Q of S comma A. Okay, and I'll mention when we go like how this would apply to tic-tac-toe in our setup, because anytime you see a Q of S comma A, that really is a V. So in our setup, Q of S comma A was the value. I'll write S plus in quotes A. That is how we're doing everything in tic-tac-toe. So it saves you a little bit of worry. And the nice thing is if there's 2 different states that would lead to the same final state, they'll have the same value, which we know is true. So that's one thing we'll do. Another thing I'm going to mention, so we're going to do something called the SARSA algorithm. Let's write some of these down so I don't forget them. SARSA, I'm going to mention expected SARSA, which might also be useful for you for the final project. Then I'm going to mention Q learning, and then I also want to mention potentially TD lambda, which is something a little bit different. Okay, but that is all good. Okay, that's what we're going to do. Any questions or comments before we start? Yeah.
So what's the difference between the capital Q and the lowercase q?
In the book or in general?
In general.
Like, why did I write a capital Q here? That's a great question. Okay, so Q learning I think is very poorly named because a lot of algorithms learn the Q function. And Q learning is one special algorithm that learns the Q function in a particular way. But the people who made it decided to name it Q learning, and now we're stuck with it. So I don't think it's a great name. That's a good question. I wouldn't be confident if they use a capital Q or a lowercase q. But so like you should put it in quotes. It's like a buzzword. Q learning. Okay. Yeah. Good question. Okay. Let's start with. Let me just recap from last class. The big idea in TD learning is don't wait till the end, right? Don't wait. TD learning. TD learning. Don't wait till the end. And if you don't wait till the end, you can learn as you go. Learn as you go. And how do we learn as we go? Well, if we move from one state to another state, we would move towards that. So v of the state S, we would push it towards whatever we saw. So plus alpha times v of alpha. Geez. Okay, v of s prime minus v of s. Okay, plus r. Okay, so this is the TD learning line. Maybe I'll write the Monte Carlo line right above it. So this is TD, and then Monte Carlo MC v of s. Okay, so these are the two lines. The first line is the Monte Carlo line, and it says you wait until the end of the episode, you calculate the total return g, and then we are going to change the value of the state s. We're going to push it towards g. So if g is higher than v of s, then we push it up a little bit. If g is lower than v of s, then we push the value of v of s down a little bit. This constant alpha learning pushes the value of v towards whatever we observe g. And the important thing is that g is only observed at the end of the episode, at the end of the soccer game, or whatever. On the other hand, TD learning, which we looked at last class, you learn right away. So you don't wait until the end. What you say is, look, I'm in state S now. We moved to state S prime, and we observed a reward R. We don't need to wait until the end of the episode to learn something. We can push the state v of s. We can push it towards v of s prime plus r, where s prime is the state we ended up in. So here, s prime equals state after s, and r is the reward we saw, the reward from s to s prime. So the reward we saw. Okay, and we talked about this last class with the example of Alice, Bob, and Carlos, where we said we should learn that Alice is pretty good at giving the ball to Bob, so we should move Alice's value towards whatever Bob's value is. They should be the same. We shouldn't have to wait until the end of the game. Okay, that was the setup from last time. I'm about to tell you what SARSA is, which is the same kind of situation, but not for V, for Q. Any questions about that before I keep going? Yeah.
If we wanted to do value function or something, we just switch to the square bracket.
This is a great point. So yes, I will get to this. When we do TD lambda, I will definitely talk about this. So if you want to know what if it's v of s semicolon theta, right? What would it be instead? And it's going to turn out to be the same thing, but you must not forget to multiply by the gradient. So both of these times the gradient, and importantly, it's the gradient at s. So in the second one over here, you might ask yourself, should I do the gradient at s or at s prime? And you want to do it at s. So that's important. We'll talk about that. That'll be when we do TD lambda. We'll talk about this. So if you're doing value approximation, you have to make sure to put that gradient on. And of course, you're updating the parameters themselves, not the value v. So it'd be theta equals theta plus all this stuff multiplied by the gradient. We're going to get to that. Yeah, that's a good point. Yeah, fantastic. Okay. Other questions? Okay, so let's see, how would this look like for Q learning? Well, in Q learning, we're not learning just the value of V, we're learning the value of Q. So Q, what is Q? Q is Q of S comma A. So S is the state we're in now. A is the action we just took. So, and that will get updated in the same kind of way. So plus alpha, and then we're going to have something here. I'll put G in quotes. It would be G if we were doing Monte Carlo. So if it was Monte Carlo, this is what it would be. In temporal difference learning, we got to replace the G with some estimate for G. What should the estimate for G be? So we're at state S. We have chosen to take action A. We move to a new state. What should we put there that is approximating G? Yeah.
V of S prime minus R of A.
So one thing you could do, yeah, V of S prime. I'm not going to write square or circle brackets because I'm just going to get confused. V of S prime, and then what did you want to do?
You add R of A. So
Plus R, yeah. Okay, yeah. So you could say R of A. I mean, in quote real life, when you're observing this stuff, if you're learning through samples, you see some reward R, and you don't know if the reward R was because you took action A or if it was because you were in state S. You see some reward. That's the word R. So this is a very reasonable thing that you could do. This is like what I would naturally think you should do. Makes perfect sense. The problem is, what is V of S prime? How do we know what V of S prime is? Right? If we're learning Q, now you're telling me I got to learn Q's and V's. And so it's kind of an issue. And so there's an algorithm called SARSA, and I'll write it out like this. SAR. What are we missing? S-A-R. We're missing the SA. We got to write SA up here. And in SARSA, what you do is you don't do Q, you don't do V, you only do Q's, and you do Q of S prime, A prime. So in other words, SA is where you started. You started at state S. You took action we took originally. Action, original. And S prime is where you ended up, where you go. And you also do one extra thing, which is you do A prime is what action you would take. What action to take. So in other words, you wait until you've actually decided on the action, and then only then do you update. If you see it in code, you'll see that the action of the next state is already chosen before we even do the update. Okay. So that's why it's called SARSA. State action, you see the reward, you pick the new state in the action, and you do it. This is the SARSA algorithm, and it's one way to do this thing. Questions or comments about SARSA? Let me switch to the other window where I have an example of using SARSA. It's with parameters. Okay, I'm going to hold off on doing it until we talk about parameters so that I can do the parameters. Okay, we'll do that in a minute. So that's SARSA. It's very similar. It's just TD learning for the Q function. Then there is Q learning. There's something completely different. What is Q learning? Q learning. Okay, so Q learning, same exact setup. We want to learn the Q function. Q of SA equals Q of SA plus alpha. And then once again, we got our G in quotes minus Q of SA. And we just put in what is G very slightly differently than before. Before we said you're going to actually pick some action that's going to tell us what G is. In this situation, we estimate it like this. We say, what would be the best possible action you could take? It's the maximum over all actions A prime of Q of S prime A prime. And then you do plus R. And so in Q learning, you don't just pick one action A prime to do. You look at all the possible actions that you could do, and you take the maximum. A better name for Q learning would have been, look, we still have SA, we still have R, we still have a S prime, so it's SARS maxa. That would have been a better name. SARS maxa. That's Q learning. I don't know why they called it Q learning. It's a terrible name because obviously everything is with Q. Everything is Q learning, so don't call it Q learning. So you take the maximum over all the possible actions. This has some pros and cons. One is depending on how you have implemented things, actually computing the maximum might be quite annoying. Like if you have to do a lot of computation, maybe if there's like infinitely many actions, now you have to do a whole maximizing thing over here. So for some implementations and some action sets, doing this maximum is actually a real chore, and like Q learning is bad in those situations because it's just a lot of work to figure that out. But in other situations, it's very reasonable and it's worth doing. And the nice thing about Q-learning is it lets you do off-policy learning. So it allows you to explore. This is better for exploring. Okay. And the reason it's better for exploring is maybe my next action, the action A prime that I would like to take, is an exploring action. Well, I shouldn't penalize the state S and the action A for having an exploring action later that is like suboptimal. I should kind of move it as if I was doing the best possible action. So it lets you explore without like hurting your algorithm too much. So that's a nice thing. It's a little bit less sensitive to that like epsilon in the epsilon greedy and that kind of thing. So it's better for exploring. Okay, so that is how you basically take the TD idea and use it on Q functions instead of value functions. Questions or comments? Yeah.
Can like all of these methods be generalized to the function approximation?
Yes, I think that's the next thing I'm going to talk about. So in the example I have, I did SARSA, but I did it with the function approximation. So let's do that now. So how would you do it with the function approximation? And the reason this is a potentially thorny issue, so before, when we did function approximation, we sort of derived our estimate. We said, think of the loss function for some set of parameters theta. You can think of that, it is like the g we saw minus the v of s comma theta squared. Okay. Okay. In real life, there'd be samples. Let me go over some set. So it'd be gi si, right? So this is what was our kind of motivation before. We said we want the function v to be matching the average value you get from state S. So we want to find parameters theta so that v of si is approximately v of si semicolon theta is approximately the expected value of g given s0 equals s. That's what we want. Of course, in real life, we can never find the true expected value. So we say, okay, you know what would be good enough is we can just replace the expected value with the sample we got. So we were in state Si, we saw the return Gi, and if we have a large enough sort of data set, like we have some huge number of samples, then this will kind of like come out in the wash, and the V function will get pulled towards the average as best we can do. And that kind of gels with how we think about square loss in stats class, stuff like that. So that was our loss function, and then we said the way to update the parameters is gradient descent. So we should do theta. That should become the theta it was, and then we should do minus alpha times the gradient with respect to theta of the loss. So this is gradient descent on the loss function that I wrote, and hopefully the loss function will get smaller and smaller, which means the v will get closer and closer to the g's we saw, which are hopefully close to the expected value of g. Okay, and if you work out what this is the update rule that we had before. Theta is theta minus alpha, and the loss function over here is gi, okay, I guess there's a 2. From doing the derivative, there's a 2. There's a sum. Let's put the sum in as well. Sum. Gi minus v of si theta. And then last but not least is the gradient with respect to theta of v. And if I wrote it like this, then there should be a plus. Okay, good. Because it's in the chain rule, the g minus s, and then there's a plus. Okay. I always mix that up. I always have to figure that one out. Is it a plus or is it a minus? You don't want to mess it up. That's an important one to get right. Okay, so there we go. That's the formula. And in practice, sometimes you don't do it as a sum because you kind of do it as you go, right? So like every single loop, you are adding on a term. This is saying I have all the samples and then I do it all at once. Okay, that was before. Now we're going to talk about how to modify this to work for TD. But questions or comments about the setup at all before we change it? So how do we change it for TD? Oh yeah.
We don't have to divide by excuse me.
Yes, this is a fantastic thing. I think, you know what? I always tell people it doesn't matter if you divide by n or not, but I think it is good practice to divide by n. Let's divide by n. I think we should. And the reason it's good practice to divide by n is because otherwise, if you double n, the loss doubles and things get annoying. If you have a 1 over n in front, then you know you can run 10 samples or 100 samples and everything will still be fine. In practice, in principle, like it's all hidden in that alpha and like maybe it doesn't matter Again, we don't actually care about the size of the loss. We just care about making it as small as possible. So it's really the same, but yeah, you're right. This is good practice to keep a 1 over n there. Okay, very good. Any other questions or comments? Okay, so let's see, how do we modify this? So one very simple idea. Here's the first simple idea. Just write the same exact thing, 1 to the number of samples, but instead of g, just replace it with v of s prime. V of s prime of I theta minus v of si comma theta. All right, very nice. So I took my g and I replaced it with the state we saw after state. This is a nice idea. And then when you do the gradient, you're going to do the gradient. You're going to get something a little bit weird looking. So you're going to have a 2 again from doing the derivative. 2, you're going to have a 1 over n. You're going to have the sum. You got v of s prime theta minus v of si theta. And then now you have 2 gradients over here. You have the gradient of v of s prime minus the gradient of v of s. So when you do the derivative, because both things now depend on theta, you don't just have 1 gradient, you have 2. I'm just realizing, I think one of the side effects, I think it's a little squished on mine versus yours. Okay, anyway, one of the side effects I think of the weirdness today is that things are a little squished. Sorry for that. Okay, and then so it's squished and I squished it, so it's extra squished. But okay, all right, you guys get the idea. So that is a very reasonable thing. Yeah.
Is the gradient of the vs prime vs inside or outside the sum?
Inside the sum. Yeah, good point. Okay. Si. Yeah. Great. Okay. Okay. This is a very super reasonable idea. If you put this in your computer, nothing will work. This will horribly fail. Can anyone think of why this will not work as I wrote it? And you don't even need to worry about gradient. What would it mean to make this loss function really small? Yeah.
I mean, like if the loss function is like, well, yeah, if the value's like linear with thetas, then the difference of the gradients would just be 0. So it's not.
Yeah.
It's never converted.
So if you do gradient descent on this, you will find the minimum of this loss function. And the minimum of this loss function will be 0. It's a very easy to minimize loss function because you can just make, for example, you can make v just a constant. Just make whatever state you put in, v equals 7. No matter what you put in, it doesn't matter. The parameters are arranged themselves so that it's always 7. And then you got the perfect score. It's exactly 0. You got it. And so this is a bad loss function in the first place. Another way to practically see what's going on is the whole point of this thing is we're trying to say, I want to know the value of this state s now. And so I'm going to nudge what we were doing before. Over here, we were saying I want to nudge the value of v of s so that it's closer to v of s prime, right? So move the value of v of s so that it's getting closer and closer to v of s prime. But if you're just trying to minimize it with parameters, there's no reason, in the way I've written it down, that the function couldn't do the opposite. So it could say, I'll make the value in the future closer to the value in the past. That would also minimize the loss function. So as written, it's completely symmetric. And so maybe what the parameters would learn is that whatever the value is in the future, you should make it closer to the value in the past. It's totally crazy, and it doesn't at all work. So whatever you initialize it to, it will just get stuck there, and it will not work. So for this reason, you have to make one small adjustment, and with this adjustment, you can't really think of it as a true loss function. So some people call it a semi-gradient. Let's write this down. Semi-gradient. Okay. And so there is no actual loss function anymore. I'm going to put a question mark here. And there is no actual gradient anymore. And to make it a semi-gradient, all you got to do is you got to cross off one term. You're going to delete this term. Delete that term. So delete the part of the gradient that is depending on s prime. And another way to think about it is this is if you make g minus v of s I comma theta squared and then you do the gradient with respect to theta, and after you do the gradient with respect to theta, then you plug in g equals v of s prime theta. Then it works. And that's the same as deleting it over there. So it's about, do you do the derivative and then plug in v, or do you plug in v and then do the derivative? And if you do it in this order, what this is telling the algorithm is that it should treat values in the future as more solid than values in the past. So we're thinking of this arrow of time, and we're thinking of values in the future have less uncertainty. We should learn those first. And values in the past, those are the things we should try to connect to the values in the future. Don't do it in the reverse. So this semi-gradient method is what is that's where we tell the computer, this is the direction we want you to do things in. Don't do it in the reverse direction. So what is the final update? The final update looks like this. We're updating the parameters theta. Theta equals whatever the theta was before. Then we do an alpha. I'll put the sign in at the end to make sure I get it the right way. And then we do, I'm just going to do one sample. So v of s prime theta minus v of s theta. Okay, plus any rewards. If you see some rewards now, put those in too. And then I do minus the gradient of theta, v of s. So at the state s, given theta. Okay, and it's minus, and I want to do gradient descent, so this comes with a plus. Okay, there we go. So that should be right. So this is the TD learning rule for learning with parameters. Very similar to the Monte Carlo rule, except you replace this with g. And importantly, you do not put any kind of s prime gradients over there. Yeah?
So how does do the same thing on the value vector avoid this problem?
How does, say that one more time?
So because when we're doing an array, because I guess we're using loss functions as a value vector, right? So yeah, never mind.
Okay. Yeah, it's true. Again, you gotta, in practice, theta is a vector. So theta is a vector, alpha is a scalar, this is a scalar as well. This is telling you, should you raise or are we overestimating or underestimating? And then this is a vector again. This is a vector that's the same size as the vector theta. And it's saying, how do you change theta to change the value of v of s as much as possible? So by doing the gradient with respect to v of s, this is what we are changing. So this is saying change v of s, please.
I guess I'm confused, when we do TD on the square brackets, how does that avoid the computer not trying to set the future values closer to the present in that case?
Yes, that is a fantastic question. That is absolutely a very good question. The way we did that here is we were explicitly only updating v of s. So we said, we're going to update only v of s. V of s prime we don't touch, but we use the value of v of s over here, or v of s prime, to figure out how to do the update. That's a very good point. So if you said, I'm going to be very clever and do two updates, I'll do one update for v of s and a second update for v of s prime, then you would run into the same issue as before, and you would have the same problem, which is that the future would become the past. That's not what we want. We want the past to become the future. Okay, yeah, great question. Okay, that is how you do it with a function, and yeah, it's called a semi-gradient method by some people. Okay. By the way, all of this is for the one-step TD, right, where you look exactly one step into the future. You're at step, you're at state S, you only consider state S prime. You could do any variant you want, 5 steps in the future, 10 steps in the future, whatever you want. It has pros and cons, right? So looking further in the future, maybe it gives more time for things to happen, right? So maybe Alice passes the ball to somebody and it takes a couple minutes until we see the situation unfold in a good way, and we want to attribute that to Alice. So more or less time is a trade-off in these TD algorithms. I'll say more about that if I talk about TD lambda closer to the end of the class here. Okay. Okay. Other questions or comments about this update rule? Okay. Let's see the example I was going to show you. So I have to open this up here. Mathematize, and then this, okay, and then the top, okay. Okay, so we're here in a collab learning about the gambler's problem. So the gambler's problem, if you remember, it is like the drunkard's walk. that we did last class. In the drunkard's walk, you either always take a step of either +1 or -1, 50% chance. In the gambler's problem, we're thinking of it as a bankroll, and you can choose, do you want to take a big bet and take a big step, like +10 or -10, or do you want to take small bets, like +1 or -1? So that was the gambler's problem. And in particular, I'm doing the situation where P heads is 30%. So you would like, you choose how much you want to bet. You will win the bet with a 30% chance, and you will lose the bet with a 70% chance. You're trying to get to $100 before you leave the casino. So you're either going to leave the casino with 0 or 100, and your goal is to figure out what sizes of bets would you place to maximize your chance to get to 100. In this example, I programmed it with only 4 parameters. So my value function, even though there's 100 states, the value at being at $1, $2, $3, $4, it only has 4 parameters. I will show you what it looks like. And okay, we have the exact answer. This is a good example because we know how to do the exact answer with value iteration because we know all the rules of this game. So I can compare the answer I get to the exact answer. So here's the exact answer for the value function. So if you're at state 0, you have $0, then you definitely lose. If you have 100, you definitely win, and it has some cool fractal-y shape in between. If you're at $50, you have right around a 30% chance to win. Actually, I think it's exactly 30%. If you're at $50, you should bet your $50, and if you win, then you win. Otherwise, the game continues. Otherwise, you immediately lose. Okay, very good. And the optimal bet size looks like this. So you should bet all your money, basically, and get this cool fractal curve. Okay, that's the exact answer. What is my value function? The value function looks like this. I'll come back to this formula in a second. It's got 4 parameters. It's a sum of 4 things. It's one of those linear value functions. I'll show you a picture of it. Here is what it looks like. Can I see a picture of it? Here we go. Why are there 4 parameters in my value function? It's because my value function is a straight line that starts at 0, it ends at 1, and it has 4 slopes. This one, this one, this one, and that one. It looks like just 3 because these 2 are actually 2 that have the same slope. So you tell me, what would you like the slope to be between 0 and 25? What would you like the slope to be between 25 and 50? What would you like the slope to be between 50 and 75? What would you like the slope to be between 75 and 100? That's 4 numbers, and then I glue them together like this, and that is a function. It's a valid function. A couple small details. One, if you put in some crazy values for the slopes, it won't get from 0 to 100. So I also rescale it to make sure that it starts at 0 and ends at 1. So I know that for sure you lose at 0. I know for sure you win at 100, and I have baked that into the way I chose the parameters for my value function. Here's the formula again for people who like formulas. So what is the formula? I take the x value, I subtract I divided by the number of parameters. So the x value goes between 0 and 1, like what fraction of the dollars you have, and I subtract I divided by n parameters. If I equals 1, that's subtracting a quarter. So it's x minus a quarter, and basically, and then I do a plus over here. So the plus just leaves it if it's bigger than 0, and it turns it off if it's 0. And so what this means is there's sort of 4 features. Over here, only the first feature is turned on, and the rest of the features, the feature for 50, 75, and 100, these are all turned off. And then the features slowly turn on. So here, 1 of them is turned on. Here, 2 of them are turned on. Here, 3 of them are turned on. And here, all 4 are turned on. So it's turning on the features one by one. This is very technically, this is what people call a spline. But this is not a cubic spline. This is like a linear spline, which probably the stats people would laugh at you for. But that's what it is. So here's the description. It's piecewise linear, has f of 0 equals 0, f of n target equals 1, and it has a slope equal to the ith weight on the interval I over n to I plus 1 over n. And that's how I set it up. So this is like an example of creating a value function, and I have built in some of the stuff I know about the function already. So I know it goes from 0 to 1. I know that it should be increasing, right? The further to the right you are, the bigger this thing will be. And I've taken those 100 states and reduced them down to just 4 parameters. Questions or comments about how the value function was set up? So this is exactly in tic-tac-toe. This is what you guys have to do, right? You have the situation. There's like 20,000 possible boards in tic-tac-toe, and you have to reduce it down to some manageable number of parameters. You don't necessarily need to use only 4. Maybe you could use even like hundreds would be fine. Okay. All right, that's the value function. How did I get the Q? That's a good question. Let's figure out, how did I get the Q? Do I also have a Q? Maybe I also have a Q. let's find out what Q is. Okay, great. Here's how I did the Q function. So this is very similar to what we're doing in tic-tac-toe. So here's the value function, v of s comma w. I use the w instead of theta because I don't have a theta key on my keyboard. You'll notice the textbook also uses w. W stands for weights, but they just mean parameters. And this is implementing the thing that I said. So you have this s over n, you're doing this thing, and then at the end of the day, it's linear, so it's an inner product of the thing. I also clip it, so I make sure it always lives between 0 and 1 by saying if it's bigger or smaller, just to reduce it down. Okay, great. And then this condition says if you're bigger than the target, you get 1. If you're less than the target, you get 0. And otherwise, you get this clipped score. Okay, very nice. So that's the V. How come I didn't do a Q? Well, let's look at what I did in Q. Let's see what I said. So I said Q function, answer equals P heads times value function of s plus a plus 1 minus P heads, value function of s minus a. So just like in tic-tac-toe, we baked in the rule that if you choose to play in index 0, then you get an x in index 0. Here I have baked in the rule that if you know the value function, the Q functions are derived from the value functions plus my knowledge of the rules. Right? So I know what happens when we bet A. I know that we're going to flip a coin with probability P heads to win and 1 minus P heads to lose. And so I can bake in the Q this way. So this is just like in your thing. I have taken some of my knowledge of the rules and put them into Q. If I had no knowledge of the rules at all, then I would just have Q of s comma a, and it would have to depend on s and a, and then over time it would have to learn the rules on its own. So you can get sort of an advantage by hard coding in some facts that you know about reality. Okay, so that's V and that's Q. And then in the example, this was what I started at. So I think I picked them sort of randomly. So that's our starting value function. And then based on this starting value function, we got this bet size. So we think, if you're at state 37, you bet $1. Otherwise, you bet these weird amounts that it's showing over here. And it's just based on where is the function like concave up or concave down, because it's comparing two values to it. Okay. Okay, how are we learning? Let's plot how let's look at the code for how we're learning. And that is over here. Okay. So here is the gradients. So I take the gradient of the value function, the gradient of the Q function. Notice that the gradient of the Q function is written in terms of the gradient of the value function, and JAX does it automatically. So when you write something like this, JAX knows what this formula is. So when you do the gradient, it's all fine. It does the gradient. Okay. We're just testing it out. Okay, here's the plot. And let me learn. Okay. So here's what we're learning. We have to do an epsilon greedy because we are choosing the actions A. If you didn't do an epsilon greedy, you might get stuck and never explore a certain thing. Every time you're choosing actions, you got to make sure you explore either by explicitly starting states differently or by doing an epsilon greedy or something else. Okay, so if there's an epsilon greedy event, then I'm going to bet randomly, but otherwise I'm going to bet the normal way. So if I go purely random, I make a random bet. Otherwise, I take the bet that is maximizing the Q function. Here's the next state thing that does the betting for me. This is like flipping the coin for me. And here is the code to do the SARSA algorithm. So how does the code work? I'm writing down, this is just to plot at the end. So at the end, you'll see a plot of how well it's learning over time. But where's the actual code? Okay, here we go. So here's the learning rate. That's what we call alpha. I put it on a schedule, so alpha gets smaller and smaller as we learn more and more, because we kind of want to make smaller updates when we know more. Here's my current action, which I choose according to the epsilon greedy. And there's my current Q value. There's my gradient. And there's my new state and my new action. So this is the SARSA in SARSA. I guess state is current state is already baked in. So state, action, new state, new action. There is no R. Does anyone know why there's no R? Did I forget the R? Yeah.
You have no ongoing rewards.
That's right. In the gambler's problem, there's only a reward at the end, so the R is 0. If the R was not there, I would also have an R. So there we go. I got all the things. And that's the semi-gradient formula. The new weights, the new theta, is the old theta plus the learning rate, Q new minus Q current times gradient. If there was an R, you would put it in here. So you do R plus this, and I guess in our situation, R equals 0. Not 90, 0. Okay, important. Okay, then we update the state. Current state is the new state, and then we repeat everything over and over again. Very kind of simple. Once you get it working, it's like not a super crazy line or anything. The hard part is kind of defining all the functions and things like that. And this is a loop, right? It's simulating as it goes, right? It's simulating and learning as it goes. In Monte Carlo, it's separated. First you simulate, then you learn. In TD algorithms, you can simulate and learn at the same time. Okay, let me show you the results. And the nice thing is, because we know the actual answer, right? So the blue line is what we think it is. The green line is the actual answer. We can plot how are we getting closer to the green line over time. And that is over here. So the RMS history is how close it is over time. So this is a plot showing me that I'm improving over time. So as I did more iterations, the RMS distance to the optimal answer is shrinking. It started out over here, and then by the time we were at iteration like 200, it was over here. And over time, you can see it improving. So here's what it looks like a little bit later, and then a little bit later, and then a little bit later. And you should see it mellow out sort of and reach a plateau. So here we're getting sort of plateau-y, and we're shrinking. Okay, and then at the end of all this training, it looks like this. So this blue function was what we found is the best possible approximation with our measly 4 parameters to this complicated green fractal. That's the best we could do. And the optimal bet sizes we found look like this. So is it great? No. Over here, we're betting $1, and we should be betting the maximum amount. And the reason is, I only gave it 4 parameters to learn something that has a lot of complexity. That's the best I can do with 4 parameters. Okay, so that is an example of SARSA and how it works for the gambler's problem. It's a good place to stop for questions or comments. All right, let me say one other really good upgrade you can do. And let me go to the textbook for this one. Let's go to the textbook. So I gotta open it and then convince the computer to let me show you the textbook. Okay, here's the textbook. And then the thing I want to find in the textbook here's some fun things we can show you. So here's SARSA in the textbook. The textbook has this cute little diagrams for states and actions, and this is the diagram that goes with SARSA, which is very nice. It's exactly what we said before. So Q of S, T, you update it to make it look like Q of S, T plus 1, E, T plus 1, plus whatever reward you saw. SARSA, okay. Q learning, same thing, but with a maximum. Very nice. Okay. Ooh, okay. I was going to talk about this one, and I didn't do it. This is another good one where if you know something about the rules, you can bake it into your formula. It's called expected SARSA. So instead of sampling just one state and one action, you do the average over all possible states and actions you would do. And so what this is doing is it's kind of eliminating some of the luck that would happen. So imagine you're at state S, you choose to take action A, you end up at state S prime, and you choose action A prime, and then maybe something really bad happens to you. Well, this is saying don't go based on that one time. Think about what would happen on average from that state, and do that instead. A good example of where this might be useful is maybe you're playing a game where there's like a dice roll or something, and if the dice roll is like comes out bad or good, it affects how good or bad the state is. You might want to use this kind of update instead of just a sample update. So update from this state, go to the next state, but then sample all the possible things you could do from there and use that instead. That's expected SARSA, which if you know how to do that, it can be a lot better. So here is some kind of plot showing that Q learning goes over here, SARSA goes over here, but expected SARSA is a lot better. It can learn a lot more, but you have to know some of the rules. Like you have to be able to compute this average. Okay, there you go. And here's the diagram for expected SARSA. Okay, I want to get to TD lambda. I guess this might be in another chapter. Oh, hey, look at this. Ooh, tic-tac-toe after states. Look at this. There, you got state S action A, state S, action A, but they lead to the same state. That's interesting. Okay, let's keep going. Bootstrapping. Okay, great. TD, this is what we were doing. Okay, what I want to get to TD lambda. Show me TD lambda. I probably can't control it. I know roughly where it is. I know roughly where it is. So I think what I want to do, yes, approximate solution methods. These are the tilings, neural networks, memory. I went too far. Least squares. Okay, maybe I didn't go too far. No, we will find it. Okay, this is it. This is the chapter that I want. Eligibility criteria. I didn't realize it was so far. Okay. So here is the graph I want to show you. This is what I was looking for. Okay. Last class we learned about TD, and we said the number of steps you look forward into the future, you can tune. So if you look one step into the future, that's this n equals 1 red curve over here, n step TD from chapter 7. If you look 2 steps into the future, that's this green curve, n equals 2. 4 steps, 8 steps, 16 steps, 32 steps. This is a nice example where, depending on the number of steps you look into the future, you have to change the learning rate alpha, and you will get a different number, different amounts of error. So it seems like n equals 4 is the best possible for this particular problem. There is another algorithm called TD lambda. And TD lambda, very similar to looking some number of steps in the future, you have this lambda parameter that is like some kind of effective how many steps in the future did you look. And that's called TD lambda. And you get a very similar curve over here. So the red curve is lambda equals 0. The green curve is lambda equals 0.4. The blue curve is lambda equals 0.8, 0.9, 0.95, 0.99, and 1. So looking many steps in the future is a lambda value really close to 1. Looking exactly 1 step into the future is a lambda value that is really close to 0. What is this algorithm? And I'm going to try to tell you that this algorithm is basically just a strictly better version of the TDN. How will I explain it? Let me. Yeah, this is great. I love this little diagram. Okay, so this is supposed to represent the arrow of time coming sort of out of the blackboard. We are currently at state st plus 1, and we are looking backwards in time, and what we are going to do is we're going to update not just the state we were just at, but all the states we visited in the past. So it's kind of like a Monte Carlo. We're at state st plus 1, and we're doing 1 step TD would be to update st, 2 step TD would be to update st minus 1, 3 step TD would be to update st minus 2, and so on. We're going to do all of them all at once. So we're going to do 1 step, 2 step, 3 step, 4 step. All the number of steps in the past, we're going to update every single one of them. Except instead of updating them all equally, we're going to do something. We're going to update the ones that are sooner more. So this one, st, gets updated the most. This one, st minus 1, gets updated second most. This one gets updated third most, and so on, which is why they have this nice diagram of a man yelling. So imagine, he's yelling. He's only so loud. This guy gets it real bad. People really far away can barely hear him. So how much of the update happens is this delta parameter that's going to control how much or how little we update. Was there a question here?
I was going to ask what delta is.
Yes, okay, so delta is the amount that you update. Okay, and here is the algorithm. Okay, before we go to the algorithm, let's write something on paper. Okay, so in the update rule, if we were updating, this is updating state S based on state S prime, this is how we update the thetas. So theta becomes that using state S. If we also wanted to update the previous step, you could also do this. You could add on, okay, we got to use a pen. So here we were changing v of S. Let's also change v of s, I'll call it s negative 1. So we could add these together, and the gradient rule, by adding on the gradient of where we were 2 steps ago, so here I'm thinking of, we got s, that's where we are, I'm thinking of now. I'm thinking of s prime, this is the future. All right, now I got s negative 1, which is the past by 1. Maybe we can also tack on an s negative 2, the past. Right? So in the classical TD, I was like, this is now. We update now based on the future. We try to make now match the future. You could also say, hey, let's make the past more like the future as well. And that all we got to do is we add on a term over here with the gradient, and the gradient with respect to theta of v of s prime, that will tell us by the interpretation of the gradient, it'll say boost the value of v of s prime as much as you can. Okay, we want the past to be updated less than now. So we want to scale it. So a very easy way to scale it is you multiply it by a parameter, and that parameter is called lambda. And so lambda is a parameter between 0 and 1. If lambda equals 0, then you update the past none, and you only update now. If lambda equals 1, you update the past and now equally. And in practice, you put lambda equals like 0.8 or something. So it's like mostly update now, but update the past a little bit as well. Then you could add on, you could say, don't just update the past, let's update the past. So v of s negative 2 of theta. Okay, let me see if I can get rid of, include v of s negative 2 in the box. But once again, we want the past to be updated even less than the past. How would we update the past even less than the past? What should we multiply it by? Yeah. Lambda squared, yes, it's the natural thing. So lambda squared, and so on. So ... You update n steps ago, v of s, let's say n plus 1, negative n, semicolon theta. So you update the past n steps ago using a factor of lambda to the n. Okay, very nice. You might think, okay, one of the advantages I said last class of TD is that you don't need to write down all these states, right? Like the advantage of TD was that you can just do the update. You don't need to keep this history of all the states like you did for Monte Carlo. And now it looks like you're going back on that, man, because you have this long formula with all the states we visited in the past. We got to write them down or something. But actually, you can just keep track of this whole sum on the fly and not keep track of the individual states. Just keep track of what is written in this box. And every time you visit a new state, you can update it. And so the formula is like this. This thing is called like delta. Okay, I'll just show you the thing now, the textbook. That way my notation will match the textbook. Okay, I gotta do a bunch of stuff. Yeah, question?
Just confirm, if we're doing like say 5 steps back and we're in the 4th, yeah, like t is equal to 4, we assume like this variable s minus 1 will be 0.
What's not 0?
Like, okay, so like if we're doing this,
Mhm.
we're gonna temporal difference, and then we're looking back more states and then half fast.
Oh yeah, that's true. Yeah, you only go back to like where you started. You can't,
Yeah.
anything past where you started, just don't include it in your sum.
So we just assume it's like 0.
Yeah, right. That's right. Okay, so how is this done? It turns out you can do this all by keeping track of something called delta. So is it called delta? I hope it's called delta. No, it's called z. Okay. Okay, great. Yeah. So z is going to be the sum of the gradients. That thing that I had in the box. Z is going to be the gradient at s plus lambda times the gradient at s negative 1, and so on and so on. How do you calculate that? Look at this line right here. So z becomes lambda times z plus the gradient now. Let's look at this formula. This is the key formula. So if lambda was 0, then z would just be exactly the gradient now. If lambda is like 0.5, it says shrink whatever z was before and then add on the gradient now. So you get the gradient now, you get half of the gradient before. And then you shrink it by half again, you're going to get half the gradient before plus a quarter times the gradient 2 steps ago plus the gradient now. And if you keep doing this over and over again, this does exactly the formula that I said before. So this is creating the thing in the box, but the beauty of it is you don't have to write down all the states, right? This is doing it in an online way. You just always keep track of the value of z, which is the same as the size of the parameters theta. This delta is how much you want to update. And then the actual update happens over here, right? So this delta is the same as the update we saw before, and then this is the actual update. So the weights W, or the parameters theta, it's the same thing. They get updated by the learning rate, but how much you should update them is this Z parameter that tells you where to go. Maybe I have one quick example I can do with this, but I'll pause here for any questions or comments. Okay, let me show you what this looks like. Let me draw another cartoon picture of what this situation is. Okay, so let's go back to the example we had before of the sparse coding. So we said, we have like one parameter here, theta 1, another parameter here, theta 2, another parameter here, theta 3, a parameter here, theta 4, and maybe, I don't know, there's a theta 5, okay? And every state in our state space, you just figure out which circles you're in and you add up the parameters. Let's suppose we had some trajectory like this. So here we were originally, then we moved over here, and 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 then something horrible happened and we get like a 0 reward, or we get negative $1 million reward. Okay, this is like some horrible state to be in. Like imagine you're driving and you crash the car, okay? It's like horrible. So now we're like, look, we gotta go back, we gotta update all these states and update the states to let them know this is a bad state to be in. Don't do that again, that was horrible. And the question is, which parameter is responsible for this mess, okay? So what we're going to do is we're going to look, theta 5, you were responsible over here one step ago. So if I look at the parameters, who's responsible? Is it theta 1, theta 2, theta 3, theta 4, theta 5? Well, theta 5 was responsible one step ago. So that was really close in the past. So theta 5 is definitely a little bit responsible. We're going to give that one responsibility to theta 5. Theta 4 was responsible but 2 steps ago. So that was like far enough in the past. We shouldn't penalize theta 4 as much as theta 5. So why don't we give it a lambda, where lambda is some number between 0 and 1. If lambda is a half, then we're saying 2 steps into the past, that is half the strength of 1 step before. 3 steps ago, we were in theta 1, theta 4, and theta 3. So theta 4 gets another lambda squared of blame. Theta 1 gets a lambda squared of blame. And theta 3 also gets a lambda squared of blame. And then the step before that, lambda 3 also gets a lambda cubed of blame. So this vector over here that we've calculated, this is like which parameters led us to this bad situation, and this is like how much we're going to update them. So theta 5 we're going to change by 1, theta 4 we're going to change by lambda plus lambda squared. Depending on the value of lambda, we might change theta 4 even more than theta 5, because theta 4, even though it only affected the final state in the past, it did it more than once. So maybe the theta 4 parameter is set wrong. So this thing is the parameter. This thing is z, and it tells you which parameters are responsible for the current situation you find yourself in. It's some combination of where you are plus like what happened in the past, and the lambda is like how far into the past you discount. Okay, so you can use this situation to update and make sure it never happens to you again by changing the parameters, and the parameters that are most responsible get changed the most. Did some of them not get changed at all? Yeah, theta 2 didn't get changed at all. I guess I didn't include this, but okay, whatever, ignore that. So theta 2 was not, maybe there's a theta 0 over here. This guy was not responsible at all. He didn't do a bad job, just leave him alone. Okay, okay, so that is how TD lambda works. And again, it's very, very easy to write down, which is why the textbook likes it. Okay. Do I want to say one other thing? Let me just quickly see. I wanted to show one potential example here. Let's see if I can find it. Okay. So, I mean, I was going to show this. There's one of the very first successes in this field is there was an algorithm called TD Gammon, which was the first computer algorithm to beat humans at playing backgammon. Backgammon is a silly little dice game. Yeah. I'm not showing it. Yes, I've decided I'm not going to show it. I'm just going to tell you what it is. Okay. Okay. There's a picture of a backgammon board. I'll let you, if you guys want to look, if you're interested in seeing how it works. It is nice. So it used a really simple, quote, neural network. The neural network had like it was a pretty small neural network by today's inputs, and it was learning by TD learning. So it was doing exactly this, and the parameters were neural network parameters, but it was doing this exact rule. Okay. Any other questions or comments? Maybe I will leave you guys with one potential hint for the assignment and or the final project, which will be the last thing we do here. I'm going to go to terminal versus ongoing. Okay, yeah, here we go. Okay, so here's the question for you to think about. I'll give you one minute to think. Okay, 10 seconds left. Put in your guesses. Oh, you can't see the timer, okay? We'll stop when we get to 2 minutes. I can see the timer. That's not helpful for you, okay? All right, we'll stop it when it gets to 2. I guess almost everyone's answered. 3, 6, 9, 12. Okay, I'm missing one person. Okay, great. Let's just do it. What did people say? Word cloud. Only terminal. Let's see. So what people said. Only terminal. Terminal only. Yes. Very good. So theoretically, you want to maximize your chance of winning. Terminal rewards only, especially true in tic-tac-toe. However, let's see. Did anybody write any howevers? One can add an ongoing reward based on whether or not the move was optimal. Only terminal. Okay. Each time you get it in 4 in a row, that's a victory point that can't be taken away. So that's an ongoing reward. So this is totally true. It's like getting victory points, especially in tic-tac-toe. It is good, but you might lose the game, right? So like if you get a bunch of points now, but then you lose the game, that's no good. So it is true, strictly speaking, all of you guys are exactly correct that there's only terminal rewards. But when you are programming it, you could make some fake rewards that are ongoing rewards to try to steer the algorithm towards what you want. And the reason is learning terminal rewards is harder than learning ongoing rewards, exactly because terminal rewards don't happen for a long time. So this whole thing we've been doing with TD learning is the idea that you want to replace waiting a long time to learn something with learning right away. And if you like sprinkle in some rewards with like what you want the computer to be doing, that might help your algorithm. So I especially think in tic-tac-toe, maybe you want to make the rewards like plus 100 if you win the game, but you get plus 1 point if you have a victory point. So if you win with a lot of victory points, you get like 110 or something. In tic-tac-toe, this might also help you. So if you're having trouble coming up with stuff, you could also potentially look at this as an avenue. Maybe I'll give, my poor computer algorithm is only getting this measly 1 cookie at the end of the game. Maybe I'll give him like 0.1 of a cookie every now and then when he does something not idiotic. All right, like that might help steer him towards the way you want. Of course, this is optional. You can totally do it with no ongoing rewards. Only terminal rewards is the technically correct answer. It makes learning a little bit harder when there's only terminal rewards. Okay, I think we'll stop there. If you have any questions or comments, please feel free to come up, and see you guys on Tuesday.